Why does reality feel solid, even when it isn't? You probably think you know the answer. You stand on the floor, you touch objects, you press your hand against a wall, and everything feels real, solid, and substantial. The world is made of things, and those things feel like they have weight, depth, and permanence. But here's the strange part. Everything you experience as solid is mostly empty space. You might think this sounds like a mistake or a paradox, but it's not. Atoms, the building blocks of matter, are made up of mostly empty space. Their nuclei are tiny, and the electrons that orbit them are far removed from the nucleus. In fact, the vast majority of every atom is just empty space. And yet, you can't walk through a wall. You can't fall through the floor. So why does reality feel solid? What's going on? This question gets at one of the most fundamental mysteries of physics. The answer lies in the fact that the universe, at its core, is far stranger and more complex than you can see. And the feeling of solidity is just one of the many tricks your brain plays to help you navigate a very peculiar reality. Let's start with the most basic building block, the atom. Atoms are made up of protons and neutrons in the nucleus, with electrons whizzing around outside. If you were to zoom in on an atom, it would look something like a tiny solar system, with the nucleus at the center and electrons in orbits around it. And the space between those electrons and the nucleus? It's empty space. Vast, seemingly infinite empty space. But if you zoom out and look at the atom as a whole, it seems like a solid object. So where does all that solidness come from? It comes from electromagnetic forces. Electrons in atoms have negative charges, while the protons in the nucleus have positive charges. These opposite charges attract each other, which keeps the electrons in their orbits around the nucleus. But here's the thing. As much as these electrons are bound to the nucleus by electromagnetic forces, they never actually touch it. Instead, the electrons create a sort of cloud around the nucleus, and this cloud has a certain size that reflects how far the electrons are likely to be found at any given moment. This cloud is what we interpret as the size of the atom. But here's where it gets interesting. If you were to take a regular-sized object, like a piece of metal, and zoom in on the atomic level, you'd see that the atoms are mostly space, with the electrons whizzing around in their orbits. And yet, when you touch the metal, it feels solid. Why? It's because the electrons in the atoms are constantly repelling each other due to the electromagnetic force. As you press your hand against the metal, the electrons in your hand repel the electrons in the metal. This force of repulsion creates the sensation of solidity. Your hand doesn't fall through the metal because the electrons in the metal's atoms are constantly pushing back, creating the illusion of a solid object. But here's the catch. You're not actually feeling the metal's atoms themselves. You're feeling the forces between the atoms, specifically the electromagnetic force that repels the electrons in your hand from the electrons in the metal. In other words, solidity is a force, not a substance. Now let's take this a step further. If you could somehow zoom in even further to a level where you could observe individual subatomic particles like protons, neutrons, and electrons, you would find that these particles are not solid objects either. They're not little balls whizzing around. Instead, they're quantum objects that exist in a cloud of probabilities. They don't have a definite position until they're measured. This is where quantum mechanics enters the picture. In the quantum world, particles like electrons don't behave like tiny balls. Instead, they exist as a cloud of probabilities, which means they could be in multiple places at once, and we can only say where they are with a certain probability. So when you think about the solid world around you, it's important to remember that this solidness is not as it seems. You don't actually experience the atoms or particles directly. You experience the forces that the particles exert on each other. And those forces create the sensation of solidity, but the underlying reality is far more abstract and strange. You're standing on the floor, and it feels solid because of the electromagnetic forces at play. But those forces are not acting on you in the way you think. They're not a simple push. They're a complex interaction of quantum fields that creates the illusion of a solid world. And this is exactly what Feynman was getting at when he said, if you think you understand quantum mechanics, you don't understand quantum mechanics. Because the universe doesn't behave the way our everyday experience tells us it should. It doesn't conform to the simple rules we use to navigate our daily lives. It operates on a deeper level, one that is far stranger and more mysterious than we can perceive with our senses. The universe is not made of solid objects. It's made of forces, fields, and particles that exist in a constant dance of interaction. What feels like solid matter is just a byproduct of the electromagnetic forces that govern how atoms and particles behave. This should make you rethink everything you know about the world around you. You're used to thinking of things as solid, as fixed, as definite, but reality is far more fluid and uncertain than you ever imagined. Once you start realizing that solidity is a consequence of electromagnetic forces and the structure of atoms, something else becomes clear. The universe is not as fixed and stable as it seems. It is, in fact, a web of interactions, forces, and probabilities, all working together to create the world we experience. This realization forces you to confront a key idea in physics. Everything is in constant motion. At the atomic and subatomic level, nothing is truly still. Atoms are vibrating, electrons are moving, and particles are interacting with each other in a constant exchange of energy. Even though you might think of a solid object like a rock as being still or stationary, at the atomic level it is anything but. The molecules in the rock are constantly vibrating. The electrons are constantly moving, and the whole structure is in a dynamic state. This constant motion is what allows forces like electromagnetic repulsion to create the sensation of solidity. When you press your hand against a wall, you're not just pushing on a rigid surface. You're interacting with a system of molecules and electrons that are in constant motion, and it is that motion that resists your hand, preventing you from passing through the wall. So the question arises, if everything is constantly in motion, what gives us the experience of stability and solidity? The answer lies in how the forces that govern the interactions between particles behave on a larger scale. In the macroscopic world, the forces are largely balanced. The electromagnetic forces between the electrons in your hand and the electrons in the wall prevent you from passing through. The gravitational force between you and the Earth keeps you anchored to the ground. And even though everything is in constant motion at the microscopic level, these forces are strong enough to create the illusion of a stable, solid world. The reason you experience solidity in the world around you is because of the stability of force interactions at a large scale. On the level of everyday objects, the quantum uncertainty and constant motion of particles average out. The repulsive forces between electrons become stable enough that you feel a consistent, solid resistance when you touch something. However, if you were to zoom in far enough, at the scale of individual particles and atoms, you would see that the world is not solid at all. It's a dynamic, fluid system in which particles are constantly shifting, repelling, and interacting in ways that you cannot directly perceive. And yet, That fluid and ever-changing dance of particles is what gives rise to the sensation of solidity. This is one of the great mysteries of quantum mechanics. How can a world that is in constant motion, that is governed by probabilities, give rise to something as stable and predictable as the ground beneath your feet? The answer lies in the concept of emergent properties. Emergent properties are phenomena that arise from the interactions of simpler elements, even though they may not be present in the individual components themselves. For example, the temperature of a substance emerges from the motion of its molecules. You don't see temperature at the molecular level, but you experience it as a collective effect of all the tiny molecules moving around. Similarly, the solidity of everyday objects emerges from the collective interactions of the particles that make them up. At the atomic level, the electrons are constantly in motion, but on a larger scale, their interactions create a stable force that prevents you from passing through objects. This is an emergent property of the forces that govern the atomic world. So, in a sense, solidness is a kind of illusion. It's an emergent property that arises when you observe the world at a human scale, where quantum effects average out, and where forces like electromagnetic repulsion create a sense of stability. But that illusion doesn't change the underlying reality. The universe at its core is in constant motion, uncertainty, and flux. The sense of solidity is just a byproduct of the way our brains interpret the interactions of particles on a larger scale. Once you realize this, you start to see that the world is not as solid and fixed as you once thought. Everything is in motion. Nothing is truly still. Even the things that feel the most stable, like the floor beneath your feet or the chair you're sitting in, are built on a foundation of dynamic, constantly shifting forces. And that realization is profound because it shows you that the universe is far more fluid, interconnected, and dynamic than we can ever truly comprehend. It's not that the universe is chaotic, but that it is in a state of constant transformation, constantly balancing and rebalancing the forces that govern it. And this understanding also leads to a deeper appreciation of the nature of reality itself. We tend to think of reality as something objective and fixed, something we can rely on. But in reality, our experience of the world is always shaped by the limitations of our senses and the way our brains interpret the data we receive. We don't experience the universe as it truly is. We experience it through a lens of perception that has evolved to help us survive, not necessarily to understand the full complexity of the world. What Feynman was getting at, and what he was urging us to recognize, is that reality is not as simple as it seems. It's not the solid, predictable world that we feel and touch every day. It's a vast, intricate web of forces, interactions, and probabilities, all working together to create the experience of stability and solidity. But underneath it all, there's a deeper, more complex reality, one that's constantly shifting, dynamic, and full of mysteries that we've only begun to uncover. And that is what makes the universe so fascinating. The more we learn, the more we realize how little we truly understand. The universe is not as we see it. It is far more strange, more beautiful, and more complex than our senses, or even our most advanced scientific instruments, can fully capture. Once you accept that reality is not as solid as it seems, a whole new world of understanding opens up. Everything you experience, touch, sight, sound, even time, can be understood not as fixed entities, but as emergent properties from deeper, more complex processes. What you feel as solid matter is not the whole story. What you experience as time flowing forward is not the whole story. What you understand as space is, in fact, a warping of a much more complex structure of the universe. One of the fundamental concepts that Feynman tried to get across to us is that the universe is not necessarily intuitive, even though we live in it every day. It doesn't conform to the simple patterns our senses are tuned to detect. We interpret what we experience based on our instincts and biology, which have evolved to keep us alive, but not necessarily to understand the full complexity of the cosmos. The reason why reality feels solid is because it's consistent. It's a set of relationships, forces, and interactions that we experience as fixed and stable. But as we dig deeper into the nature of reality, we begin to see that nothing is truly fixed. Everything is changing, interacting, and subject to deeper forces. Take the example of gravity, a force you experience every moment. It's not a simple pull from one object to another. It's the curvature of space-time itself. This is a difficult concept to grasp, but it's one of the fundamental insights of Einstein's theory of general relativity. Instead of thinking of gravity as a force pulling objects together, think of it as the result of mass warping space-time. The more massive an object, the more it distorts space-time around it. The Earth, for example, bends space-time in such a way that everything near it moves towards the center of the planet, creating what we perceive as gravity. When you drop an object, you're not just seeing it fall. You're witnessing the way space-time around the Earth curves, guiding the object toward the planet. The object isn't falling due to an invisible force. It's following the curvature of space-time that the Earth's mass has caused. That's the underlying truth. Gravity is not an invisible pull. It's the bending of the very fabric of space-time itself. And your experience of it, standing on the ground, feeling the pull toward the Earth, is just an effect of the way space-time is structured around you. This is not intuitive. Our everyday experiences don't prepare us for concepts like these. We feel gravity as a constant pull, but it's only through a more rigorous understanding of physics that we see it as a warping of the very fabric of space and time. And this is just one example. Every force in the universe is more complicated than our senses lead us to believe. Let's take another example: light. We see light every day, and it seems so familiar. It travels in straight lines. It illuminates the world around us. But light is far more than just something that helps us see. In fact, light doesn't travel in straight lines at all times. It bends, it interacts with matter, and it behaves both like a wave and a particle. This is the wave-particle duality of light, a concept that's central to quantum mechanics. Light, when it interacts with matter, behaves like a stream of particles called photons. But when it's traveling through space or passing through a medium, it behaves as a wave with crests and troughs that can interfere with each other. These waves can add up, creating stronger light in certain places, or cancel each other out, creating darker regions. This wave-like nature of light is responsible for phenomena like interference and diffraction, which we see when light passes through small openings or reflects off surfaces in specific ways. The particle aspect of light is evident when it interacts with matter. This is what makes the photoelectric effect possible. Light hitting a metal surface can knock electrons loose, but only if the light has enough energy or frequency. This behavior is so strange because it doesn't fit with the traditional, classical understanding of light as just a wave. It's a fundamental characteristic of light that defies the simple view we have of it. But quantum mechanics tells us that all matter, not just light, behaves this way. Particles like electrons and quarks also display wave-like properties under certain conditions. In fact, electrons don't have a definite position or velocity until they're measured. Instead, they exist in a cloud of probabilities, and only when you observe them do they decide where they are. This leads us to another paradox. The universe doesn't behave in a way that we intuitively expect. At the microscopic level, the rules are very different from what we experience in the everyday world. Atoms, electrons, light, they all follow a set of laws that don't conform to the simple, predictable rules we see in our daily lives. The result is a world that's full of strange phenomena, things like superposition, entanglement, and the uncertainty principle, concepts that challenge our understanding of reality itself. Feynman was deeply aware of this. He understood that the universe is not a simple machine that behaves predictably. It's a complex web of interactions governed by laws that are often counterintuitive and mysterious. But even though these laws seem strange and difficult to understand, they are remarkably precise. They describe the behavior of particles, waves, and forces with extraordinary accuracy. The key to understanding the universe, Feynman would argue, is not to look for simple answers. It's to embrace the mystery. The universe is strange, and it doesn't always make sense. But it's beautiful, and its complexity is part of what makes it so fascinating. Now you may be wondering, what does all of this mean for us? It means that the way we experience the universe is not the whole story. Our senses are limited. They give us a version of reality that is useful for navigating the world, but it's far from complete. The universe is far stranger and more complex than we can see. And to understand it more fully, we need to step outside of our everyday experience and explore the deeper laws that govern everything. The beauty of science is that it doesn't just give us answers. It opens up new questions. It challenges our assumptions. It forces us to rethink what we know about the world and about ourselves. The more we learn, the more we realize how much we still don't understand. The universe is not as we see it. It's not as we experience it. But through science, we can begin to uncover the deeper truths about how it works and how we fit into it. And that process of discovery is the most exciting part. As we continue to peel back the layers of reality, one thing becomes abundantly clear. The universe is not made of objects as we typically understand them. Instead, it is made of forces, fields, and relationships. Everything is interconnected in ways that defy our intuitive sense of space, time, and matter. When we look at something solid, like a rock, or feel gravity pulling us down, what we're really experiencing is the result of complex interactions between fundamental forces and particles at scales far smaller than we can see or measure directly. Consider the most basic components of matter. Atoms. These tiny building blocks are composed of protons, neutrons, and electrons. But even atoms are not as simple as they appear. The majority of an atom is empty space. The nucleus, made up of protons and neutrons, is tiny compared to the space around it. The electrons, which orbit the nucleus, are spread out in what we call electron clouds. And these clouds themselves don't have sharp, defined boundaries. The electrons are constantly moving and interacting in a way that we can't predict with absolute certainty. You're probably familiar with the idea that atoms are mostly empty space, but it's worth emphasizing how strange that truly is. Here's why. You and I, and everything we see around us, seems solid. We can feel the resistance when we press our hand against a table, for instance, or when we stand on the ground. It seems like everything is made up of hard, unyielding objects. But when you look at things from the quantum perspective, when you zoom into the scale of individual atoms, you realize that on a fundamental level, nothing is really solid. This isn't just a philosophical concept. It's an observation that has profound implications. It means that the solidness we experience is actually a result of forces at play between particles. The forces that keep atoms in place, the electromagnetic forces between electrons and protons, are what create the sensation of solidity. But these forces don't involve atoms touching one another. Instead, they involve complex interactions of charges and fields, which create the resistance you feel when you try to push through something. When we get down to the microscopic level, what seems solid and fixed is actually a dynamic network of forces. For example, the atoms in your hand are constantly vibrating. If you think about the behavior of electrons, they are not in a single, defined position. Instead, they exist as a probability distribution, a cloud of potential locations. The uncertainty in where an electron is at any given moment is not a flaw of measurement. It's a fundamental characteristic of quantum particles. This is known as quantum uncertainty. When you press your hand against a table, the electrons in your hand don't simply collide with the electrons in the table. Instead, they feel the repulsive forces due to the electromagnetic interactions between them. The electromagnetic repulsion between the electrons in your skin and the electrons in the table prevents you from passing through. But again, this solidity is not a matter of atoms physically touching each other. It's the result of the interactions of these forces. This understanding of the universe is very different from the traditional view of objects just sitting still in space. Instead of fixed hard objects, what you experience as solidity is really just the result of a system of forces that resist compression. It's a dynamic process, not a static one. Now let's think about time and how it fits into all of this. You experience time as a constant, unbroken flow. Seconds pass, minutes, hours, and days. But when we examine time more closely, we find that it's not as simple as we assume. Time doesn't pass at the same rate everywhere. It's not a universal experience. Time is relative. That means time behaves differently depending on where you are and how fast you are moving. This is one of the most famous insights from Einstein's theory of relativity. He showed that time slows down for objects moving at high speeds, especially as they approach the speed of light. This phenomenon is known as time dilation. The faster you move through space, the slower time moves for you relative to someone who is at rest. If you were traveling close to the speed of light, you could experience only a few hours or days of travel, while years, decades, or even centuries could pass for someone on Earth. It gets even stranger when you consider gravitational time dilation. Time actually passes more slowly near massive objects. The closer you are to a planet or a star, the slower time moves for you relative to someone farther away from that mass. This is another profound shift in our understanding of time. It's not an absolute flowing river. It's flexible and dependent on where you are and what's around you. The implications of this are staggering. If time is not absolute, then our entire experience of the world is shaped by our relative motion and the mass around us. We don't live in a world where time ticks along the same for everyone. Time stretches and contracts, depending on your location in space-time. Now, consider light and how it fits into this picture. You see light every day, but have you ever stopped to think about how strange light really is? Light travels at a constant speed in a vacuum, 458 meters per second. But that speed is not the same in all contexts. The speed of light remains constant, but its apparent speed can change depending on the medium through which it travels. For example, light travels slower through water than it does through air. The speed of light can also be affected by gravity, as described in Einstein's theory of general relativity. This should make you question everything you thought you knew about the simplicity of light. We think of light as something that moves instantaneously across space, but the reality is much more complex. Light is subject to the curvature of space-time. It doesn't just travel freely through space, it interacts with the very fabric of the universe. And then we get to quantum mechanics, which takes everything we thought we knew about the universe and turns it upside down. Quantum mechanics tells us that at the smallest scales, particles don't behave the way we expect them to. Particles can be in multiple states at once. This is known as superposition. A particle can exist in two places at the same time, and it's only when we measure it that it chooses a specific location. The act of measurement collapses the particle's wave function and forces it into one of its possible states. Quantum mechanics also introduces entanglement, a phenomenon where two particles become linked so that the state of one particle instantly determines the state of the other, no matter how far apart they are. This instantaneous connection between particles seems to defy the speed of light and the limitations of space-time, suggesting that the universe is more interconnected than we can fully understand. This world of quantum mechanics is vastly different from the everyday world you experience. In your daily life, things are predictable. You can measure distances, calculate speeds, and make accurate predictions about the behavior of objects. But at the quantum level, nothing is certain. Everything is probabilistic, and this uncertainty is not a flaw in our knowledge. It's a fundamental aspect of the universe. Comment below. What part of the universe still feels the most mysterious to you? I read every thoughtful response. Subscribe for more deep dives into the truths behind the universe that challenge what we think we know.